Thank you, Iran. Thank you all for staying for the very last session. Thank you, the organizers, both for the workshop and this wonderful conference, bringing together somewhat different communities, actually. And so if we talk about coupled molecules, artificial molecules, I want to start from artificial atoms. These are results from basically my first paper starting as a senior lecturer in Jerusalem, where together with Oded Milo, we took indium arsenide colloidal quantum dots and using STM can demonstrate directly the artificial atom character. Spherical particles, so you can really see in the IV curve the band gap, and at the conduction band side, where current increases in the step-like manner due to the S-like state. So you have twofold degeneracy of the S-like state borne out by this charging effect, two electron tunneling through the S-like state, and then there's a larger separation until you hit the P-like state, which is six-fold degenerate. That's because of the spherical symmetry. The narrow gap of indium arsenide was actually critical to be able to do these kind of measurements, and you can even image the wave functions. So in core shell nanocrystals, if you put the bias above the S-tip peak, then you get a spherical-like image of an S wave function. In the middle of the P manifold, the current image will then have this px plus y bagel-like shape, which then actually emerges into a total spherical shape again when you are at the edge of the P and sampling all the P states with your current image. So that's the basis, so let's keep this in mind. In the meantime, since then, 2 decades and so on, these kind of particles with a concerted effort of the community has really made it into a large-scale, very, very demanding display, which brings me to be very optimistic for the future additional applications of such systems. This is the display world where quantum dots can go inside, or now inside. Millions and millions of units are being sold, not just by Samsung. So the general idea, this is what we see in the color chart. These are the standard screens that you have. Actually, you can see this difference when you look at this crappy, image of this projector versus even there was a screen here. But when we had a screen here, you could see this very clearly. It was in the other hall, I think. The difference in color. So, anyways, with these quantum dots, this is a very demanding application. You have to have the right color. It has to be very narrow. It has to be able to be stable for a decade, working continuously. And all this has been made with these nearly unity quantum yield particles. So that's a good sign that we can even make them on a large scale, like thousands of kilo scale, tens and thousands of kilo scale over the years been accumulating in all these screens. Okay, so what next? We got it. We have technology, we have science. So, okay, now comes the analogy to go into molecules. We've heard a lot about artificial molecules here, but what I want to have a molecule in which I will have hybridization effects. I want to have hybridization effects of the wave functions, bonding and antibonding state, putting quantum dots together, enriching the possibilities, the functionalities of such materials when we use those as artificial building blocks, artificial atoms. And yes, we had all this week so many interesting talks. We saw the amazing geometrical control achieved, especially for gold particles. This is where it started. We heard these talks from Chad and others. But you know, when you have the DNA link, this is very good for metal particles. You will have plasmonic effects. You will have electromagnetic effects. You can have dipole-dipole coupling, all those things, maybe energy transfer, but you will not have wave function hybridization, right? You know, tunneling, electron transfer is very difficult across these kind of bridges. So we need something different. This is not useful somehow for wave function coupling. So the concept that we came up with is to take core shell nanocrystal, and this is my model system, cadselenide, cadsulfide. Now I have this potential. I'm going to bring them together, but I have to fuse them, and then I really have a double dot. I have a molecule, so to speak, artificial molecule. That's the idea. And indeed, this gives us a lot of control because, you know, in this, we can still change core size. That will give us different emission color, like we have in quantum dots. We can control the barrier. We can control the barrier by the thickness of the shell. That will dictate the distance. And then I will show you that we can also fill up this neck. The constraint between them will also dictate the tunneling of the wave functions in between those two centers. In the future, you can think about different cores. I will show something about that. That's very interesting. You'll have two-color emission suddenly from a particle, potentially. And I will show a result about that at the end of my talk. We can then think about other type of band alignments, like separating the charge. For example, having a type 2 band alignment instead of quasi-type 2 or type 1, typical of the cat selenide cat sulfide model system. At the end, this is a quantum dot-like system in the sense of surface manipulation, in the sense of what we can do with it after we have made this. It's just like what we have learned throughout all these efforts on quantum dots. We will be able to do this. For example, put it within a plastic sheet to embed it in a screen, print it for pixels, put it in biology, whatever, okay? That's the idea. I will be very brief about the chemistry because I actually talked about it in the workshop, and this is now about functionality, but just to put you into line with what we're doing. The way we do it is a template-based approach. These are silica particles serving as the template on which the chemistry is done. 200 nanometers, these are the quantum dots bound to the surface. We then fixate them with a very thin layer of silica and also blocking other sites, binding sites on the surface. Then we use a tetrathio linker. We add it into the solution. And then we add again the batch of the quantum dots. Therefore, they bind on the surface, in principle forming dimers on the surface. The next step is etching away selectively by HF the silica, which releases the dimers. These are not pure dimers. We have a separation. We need to separate monomers from dimers. Psi-selective precipitation with solvent-non-solvent consideration is very good for this because the difference in volume between monomer and dimer is really large. So that easily separates somehow, and you see a purified version. This is the non-coupled bound version with the organic linker. In this one, I will not have the strong coupling that I'm looking for, or essentially will have weak tunneling effects. I can still have energy transfer and so on. And then comes the really interesting fusion phase, which I talked a lot about during the workshop, where we heat up to moderate temperatures, 200, 240 degrees centigrade, yielding a continuous lattice linking and fusing the shell, which is a similar shell material, cat sulfide in this case, bridging both for smaller core shell quantum dot or larger or smaller quantum dot systems, okay? So that's how we do it. And at the end, characterizing this in a high resolution stem, we see continuous lattice. We see in the elemental analysis very clearly that we still have this core shell architecture. So we maintain the core shell architecture through all this processing. And now, okay, we have the system. Let's look at fundamental hybridization effect. First of all, what we can expect from simple effective mass-based calculation, solving the Schrödinger equation for this system on a grid with COMSOL. And so looking just at the S state of the electron, which is a light effective mass here, small band offset, it will split into bonding and anti-bonding state, and we can calculate that. And I'm just showing one result for what is the effect of constraint of this neck. So when we are here, the neck thickness is 0. Yeah, this is kind of like what happens when you have a organically linked system. The coupling energies are very small. Not surprising, you cannot tunnel in between. When we increase this neck and fill it up and have almost a rod-like particle, the other parameter that's shown here is the band offset. And the band offset also affects the energies, but we see the energy scale of 10, 20 millivolt splitting between bonding and anti-bonding states for the electrons, so there are predictably hybridization effects. And we can actually do this experimentally also, just a little bit more about the chemistry, that we can actually control the neck thickness by the fusion conditions. So when we increase the temperature between 200 to 240 degrees, this is more or less the onset of this kind of fusion effect. When we increase the temperature, we can gradually fill up the neck, also reducing amount of excess ligands. And the model we have in mind for this mechanism is to have intraparticle ripening, that atoms are moving into this higher energy neck region to fill it up, to fill up the neck. Okay, that's the idea. And this is accompanied by a redshift, qualitatively in agreement with what we see from simulation, at least for the hybridization. Okay, overall it's more complicated because This is what I talked about so far, just the electron, but we have a hole and we have Coulomb interactions. And Coulomb attraction will actually induce some binding or not binding. It depends on the detail of the system. In this system, actually, there is a strong effect of the hole. Because the hole is much heavier than the electron, the band offset is large, so it doesn't really hybridize. It doesn't hybridize. It can either go to one side or the other side. And then, if this is the separate wave functions, once we introduce also a solution of the Poisson equation in an iterative manner for the effect of one charge on the other wave function, we will have some localization on one side. It still spills out to the other side, but much less than before. And still, overall, we do have a redshift. We can calculate, and the prediction is quite good in agreement with what we see. So large core shell does not show significant redshift at all. The smaller ones do show 10, 12 millivolt shifts. You can say, oh, this is not a lot. Yeah, it's much less than a hydrogen molecule. But, for example, the comparison point could be MBE grown dots, which are larger. And in those systems, the typical splittings and shifts are, millivolt, 1 millivolt or sub-millivolt scale. So these are only relevant for low temperature. And we can see these effects at room temperature. Also, we can reproduce the redshift from experiment versus this calculation for the neck filling effect, which I just discussed. Now, that's the hybridization effect. A much better and more elaborate calculation was done by Eran Rabbani, guiding Leo Verbitsky, who did his master's degree in Jerusalem, actually, at the time. And there are two things to take from here. This is a fully atomistic model. You can ask around about the details. But that means, for example, you could compare what happens if you link different facets. These are word-side particles. They're not so different in their dependence. There is some difference. These were the particles I've shown you, these triangles, the red triangles, very much in matching with a full atomistic calculation. And what brought something nice to our attention is, hey, we have a very thin shell, and we predict to have 80, 100 millivolt shifts. We didn't start with these very small particles. They're more difficult to handle. This is just 4 or 5 nanometers, and also difficult to really characterize in the TEM. But now, after this, we put the effort, and you can see, very interestingly, that this is what happens. These are the pristine nanocrystals, then we fuse them. So you see we have this tail. Now you see what size selection does. We do have here another peak emerging. As we do more cycles of size selection, we improve the purity of dimers versus monomers, and the contribution of the dimer emission increases on account of the monomer emission, and there you can see this 80 millivolt shift, which is quite in good agreement with what Eran predicted in the calculation. Here it is. So we do have hybridization effects. Okay, that's nice. We have a hybridization effect. You know now about the synthesis. What next? So really, this is a very interesting system for many body interactions. Biexciton states are the first ones to consider. We have here the opportunity to have a segregated biexciton or maybe localized biexciton. And why are biexcitons interesting? Not only for the basic many body. It is, as we will hear, I'm sure, from Victor later, the lasing threshold in principle. So this is a very interesting kind of state for quantum dots. And also, on the other hand, it quenches, in the monomer, it will quench because of increased Auger effect, non-radiative Auger interaction with all these charges in the same volume. And that's not so good for lasing maybe, but it's quite good because it enables thinking about monomers as single photon emitters, because 2-photon emission is quenched due to Auger interaction. How do you study biexciton? So at first level, we do it on a single particle basis. The classic way to prove if you have anti-bunching of photons is the Hanbury-Brown twist configuration. You have this beam splitter. This is the stream of photons coming, split into 2 avalanche photodiodes. If you really have a single photon emitter, there will not be at the same time, after one pulse, simultaneous emission in clicks in both of these detectors. And therefore, when you plot the G2 contrast here, or the G2 function, this being the G2 contrast, you will see this contrast between what happens after 0 time, or at 0 time the correlation is 0. And this means high contrast. And if you have 2 photons coming at the same time, you will have sometime 2 clicks one and one, both detectors will click. And actually, it was shown by Munji Bawendi, for example, that this contrast, this ratio of this peak versus that peak is the quantum yield of biexcitons over the quantum yield of the exciton. The quantum yield of the biexcitons is pretty low in monomers, and indeed, you can see that when we look at a monomer, this is really the typical G2 measurement for monomers on a single particle basis, where you have quite good contrast of less than 0.1, criteria for single photon emitter less than 0.5. This is well within the single photon emission criteria. And that is because the situation of two photon pair, biexciton on a monomer, is really a situation where Auger relaxation, non-radiative Auger, wins out versus the emissive rate of a biexciton. What happens in our dimers? Well, we saw completely somehow different behavior for these dimers, where you see that now the G2 suddenly becomes very high or much higher. We do have some photon bunching. And that brings to mind that now we have a larger volume, a particle. We could have this type of a configuration of a segregated biexciton, yeah? And that could be emissive. The quantum yield of the exciton is actually somewhat compromised, perhaps, because we also have charging, which could be compromising the quantum yield of what is called the single exciton emission. And so that was the first level of measuring these effects of biexcitons. Now we can do much better. We can look at the monomer. You have the biexciton, G2 contrast. You can see blinking effect, on-off blinking, which is typical, the off state being, for example, a charged state, which turns the particle off, also because of Auger. And also, the lifetime of a single particle is very much dominated by single exponential decay of the X0, the exciton, the neutral exciton state. The dimers that I just showed you, which are not really totally fully neck, somehow we call them weaker neck, you have them showing you this G2 level, which is quite high, because of what I mentioned, that now we have all these other possibilities, maybe of a biexciton state that is emissive because of this segregated situation. Actually, when we filled up the neck, we somehow revert back to a single photon emitter status. You see the G2 went down. We have a regaining of a strong X0 component. Flickering, which is seen here, is now more or less on-off, okay? So something is happening with neck size. What we can do even better now is recent results with Professor Dan Oron and his group at Weizmann Institute, and this is heralded spectroscopy. They've introduced this idea of using an avalanche photodiode array instead of Hunbury-Brown twist. Much more information. And what is heralded spectroscopy? To herald is a sign that something is about to happen. Herald Tribune. Very hard to find positive headlines in newspapers. Okay? Hamevaser is in Hebrew. This is an ultra-Orthodox Jewish newspaper, by the way. And I live in Mevaseret, Zion. Zion is one of the names of Jerusalem. One hill before Jerusalem. If you go up to my town, that means you are almost there in your pilgrimage to get to the Wailing Wall or wherever other site you want to see in Jerusalem. So that's the idea, and that's why we are using heralded spectroscopy, because what we get is three things. First, we now have, dispersing the photons, both information of the energy of the photon that arrived. That's first. Second, we have the time information, which we need. And third, we can specifically follow pairs, just pairs. We can either follow single photons or pairs, but if I'm after a biexciton, I want to follow pairs. And that means that I can really determine very nicely the energy and lifetime of the first exciton in the biexciton pair, of the single exciton that's remaining there, etc. That's what we are using, and we will look at monomers, fused dimers versus non-fused dimers. Those are the three systems which we could in principle compare. And so this is a bit elaborate, so sorry, but this is the typical result of a single particle. Okay, these are all the photons, which are dominated by the single photon emission in this case. And now these are the first photons in the pair of the monomer, the first photon in the biexciton, and you see this is very clearly blue shifted. Blue shifted because in this system, this is a quasi-type 2, we call it. Namely, the electron is spilling out, the two electrons are spilling out, the holes are localized. So the repulsion between the two electrons and the two holes is overcoming a possible attraction. So it's not a bound exciton, a biexciton, it's like blue shifted. And this is the amount of shift. We know the lifetime of this exciton is very fast because of this fast Auger, 300 picoseconds. G2 actually for this system is 0.1, like before, 0.09, very low. What happens in the segregated case? In the case where we have only a linked system, it's not really fused. You cannot really move from side to side, right? You think about it, not easily at least not by tunneling. And then we see a lot of pairs. This is really dominated by pairs. They are not really shifted from the total emission because it's basically the two particles emitting, right? Either this one or this one. The biexciton is not quenching. There is no Auger, significant Auger in place. Indeed, the lifetime is quite long. What happens in the fused dimers? Here we have actually kind of a situation where we see both effects to some extent. Namely, some of the particles are really dominated by the situation of like a monomer. So it means that we have a localized biexciton on one side. But actually, there are about 30% that have a combination of both a fast component which is actually a localized biexciton, minus 30 millivolt of this shifting peak. And also the lifetime is very short. It's just like this case. But also a proportion which is more like the segregated case. Long lifetime, 11 nanosecond, and almost no shift. Okay, so it's coexistence of these two biexcitons. How does this work? This is the statistics now on numerous tens of particles of the monomers. You see the blue shifted repulsive biexciton in the system where we only have a fast component. This is now distributing between fast and slow components. In the non-fused case, we have a little bit of the fast component, but mostly dominated by the slow component with no shift of the energy. And in the fused dimers, this is where you see fast component, which is more or less like monomers, but also quite a nice component of slow excitons, which is hardly shifted. We were aided by this team of Professor Clemente and Planales from Spain to calculate the energies of biexciton states. First of all, in monomers, this is the dependence on the core radius for this negative binding energy, like the repulsive energy. It's well in matching with our core radius on the order of 35 millivolts. That's the binding energy, which is twice the single exciton minus the biexciton. And however, if you go now to a homodimer and you consider the segregated case, which is the slow component, this will predict zero binding energy in a really pure homodimer. How does this work out with our result? Is that really if you just change a little bit in the calculation, the radius of the core, these are 0.1 nanometer, 1 angstrom. It's less than what we can do experimentally. A layer is 3 angstrom. Then you already have the effect of a heterodimer, so to speak, in this energy scale. Namely, the large particle, the bigger core, dominates, and really this becomes like the favorable lowest energy state that the theory will give you as will have this repulsive character. Okay? And really pure homodimer is more difficult to find, even in a good distribution sample as we have. But it's really interesting experimentally what we do here. Now we plot the data. G2 is a measure of the neck. Remember, the G2 is a measure of the neck. Low G2 is a more rod-like particle which is delocalized. Monomers are here, very low G2. They only have a fast component. This is the relative contribution of this slow component. So they don't have any slow component. Nothing can segregate in a monomer. And the non-fused dimers, where we cannot have this tunneling, are up here. They have a high G2, and almost all of them are slow. But in between, we have this control where we have the combination, possible combination of a slow and fast component. And this is the picture now to think about. 2-photon emission, oh my God. Non-fused weak neck dimer will show segregated emission of couples. Here we just have Auger, so we just see single photon. And when you go to the rod light, you have a combination of the two. And the implications are that this can be a tunable system for either single or bi-exciton emission, depending on the synthesis parameters. Okay. Now what else we can do? So synthesis property now, something which will be an instantaneous color switch. Think about heterodimer, green, red. Can we switch green and red emission? And this goes to actually useful things like maybe displays with a switchable pixel, tunable lasers, two photon or tunable single photon emission. And electric field is a way to do this. So under a field in monomers, what you can do in these kind of quantum dots, you basically can tune the emission somewhat, but you see the electron is going to one side, the hole to the other side, and that means that you also change the overlap. So the lifetime will now increase, and the radiative lifetime, and you will maybe suffer from intensity loss. And nonetheless, people have really considered, including Sasha here, to use the usefulness of quantum dots possibly as color agents, sensors for electric field fluctuation in neuronal systems, okay? And there has been some work on that. I will go fast now. So we look at now the electric field effect. This is my student Jonathan. These are our electrodes, interpenetrating electrodes, 3 micron spaced. These are particles in between those electrodes. We now apply the field. This is a monomer. Nothing much happens between 0 to 180 volt. A little bit. These are pretty small, so you cannot move the wave function too much around. In the dimer case, we see quite differently case. This is a dimer, 2 emission centers. 0 volt, it's quite broad, and here, and then plus 180, you see it becomes narrow and shifted to the blue here. And so how to interpret this is that really we have 2 emitting centers, and at 0 volt, they are kind of emitting together. I call it red and green, even though you cannot really see the resolution. But when you apply the voltage, the electron is sloshed around to this blue side, so to speak, or green side, and this increases while the other side reduces in its emission. Okay, so this is now very different from single monomer emission. We asked ourselves, we want to be sure that this is actually what's happening. This is, by the way, a real-time image of the CCD, where the emission fluctuates. And now, if we look to verify this being monomer and dimer emission, we go to the optical image. We now go into the focused ion beam, identify this region with our markers. We cut out a lamella of this layer, go into the TEM grid, and here is the TEM image of the same thing. This is what we call this dimer and monomer, and indeed at high resolution you can see the dimer, you can get its angle relative to the electrode, and this is the monomer. So we are sure that this is monomer versus dimer. So that's a correlation. What's happening? How does it switch? So this is what's happening. This is small versus big particle, green, red. And under the field, the hole does not respond in the same way of the electron in the system. The electron can slosh around easily. So on one side, if the plus is here, if the green side dominates. If we change the bias, the other side dominates. That's the principle of switching. We can simulate this effect by looking at the overlap of the wave function based on applied field. And if you have the hole on this side, for example, at some point, the overlap becomes switching to the other side. The electron is switched to the other side, so there's no overlap, so only one side, green emission. If the hole is in the other side, you consider the overlap on this side, you get the red emission, which switches over. Okay, that's the idea. And it is correlated also. The effective switching is correlated also again with the neck, with the G2. This is the correlation which I now need to speed up. When we had back the paper from revision, some comments related to the switching is over a very small range. So we went into an effort of trying to do not so well controlled, but mixing to make heterodimers. So this is a case of red and yellow, let's call it. You see the 2 peaks at 0 volt. And when you apply the bias such that you attract the electron to the red side, you see that we increase this peak over this peak systematically. And oppositely is what happens on the other side. And this is how now it looks. It switches between, the single particle switches instantaneously between 600 to about 660. This is an example of, so to speak, more green and yellow. And again, you can see this ability to change the relative intensities by applying and changing the bias on this dimer. So the vision is that this can be perhaps a switch, color switch, I don't know, maybe for a pixel setup that you, now instead of RGB, you can have a joint RG pixel where you kind of switch between red and green emission of the same dimer or a single photon source. Okay, I'm reaching to the end, which means that I try to show you we now have a way to make coupled dots. We want this bridge. This crystalline bridge is important to have really coupling and hybridization and energy, electron transfer effects, etc. It then becomes very interesting system for many body interactions. And it's possibly maybe also a color switch is one first idea we had with this system. Maybe there can be more. And I really think that hopefully we can do this for other systems. We're working on it. So it's a basis where you have different building blocks. We can change sizes. We can change core shell band alignments. And I think there can be a potential to make further functionalities with such coupled dot systems. And at the end, I want to thank my group here, a very dedicated group of students. These alumni started the project, the cooperation that I've tried to mention, and funding agencies. Thank you for your attention.
Thank you, Uri. I'll quickly ask you a question to get it started. But why don't you use all the nice DNA chemistry that we heard to actually bind the two particles? Why do you need to reinvent it?
It's not a planned question. Well,
I'm asking a synthetic question, of course.
You know, I mean, the distances, we have to, the stage which I'm really interested in and is very critical for this is the fusion step. And we need, I think, we didn't try to do it with the DNA link system, but the distance over there is quite large. So the linker is not very long. The linker that we use is maybe 1 or 1.5 nanometer. And in those conditions, the particles are already touching, and it's also sustainable that at high temperature, 200 degrees C, okay, those DNA links will, I'm pretty sure, break up, but the molecule still sustains this. So these are core shell growth conditions for nanocrystals. And then you can still have chemistry, which you can do in order to get this fused step. So fusion was the critical step for us. Rather,
yeah, I understand.
Yeah, that's the main thing. Yeah, yeah.
So this might be a naive question, since this is not my field, but I don't fully understand why you don't get a shift in the monomer case, because don't you get something like the quantum confined Stark effect, you know, that people see for gallium arsenide and gallium aluminum?
You would get a shift. You do get a shift in some monomers. These are small monomers, so the core is quite small. So the amount that you can move around is very small. So some of the monomers do show a shift, but it also maybe depends on the orientation of the C-axis. It's a Wurtzite lattice, etc.
What is the field, Uri? You said what the, do you know what the field is?
It's 180 kilovolt or 100 kilovolt over 3 micron. So those are the field intensities that we are using. And the extent of shift, now that we have these heterodimers, if you think about it, it's not a shift, it's switching, so it's a different effect. But then it's over a much larger range, which you compared to what you could achieve even with nanorods. So what people have done, and we have these experiments also, that under a field you can use a nanorod, you have a more volume, and then you can get a larger Stark effect actually, if it's oriented in the long axis along the rod. But here, the main point is that it's a switching effect rather than a shift and change of overlap in a sense. The idea that you still maintain overlap of electron and hole on one side or the other side, so the intensity is not supposed to change too much when you switch from side to side. Yeah.
Is it possible, thanks, Uri. Is it possible to imagine making, you know, trimers of different conformations or making long rods of these, or is it interesting to do that? And is it interesting to imagine self-assembling lots of these dimers into organized patterns?
So going to the next level of complexity in these kind of artificial molecules. For example, a trimer, I still have to think which kind of trimer might be interesting. On a chain, we did have some thoughts. So there are these, what is called QWIP, quantum well interference photodetectors, which is based on a series of quantum wells, and then you have you're basing on the intraband transition, which is in the IR. So could you do that with a chain of particles, for example? So I think chains could be interesting, maybe trimers too, but it's too early to say. This kind of chemistry has some limitation in selectivity and so on, but I think that there will be improvements in this as well. I mean, we're working on some, and I hope others will join on that effort.
I just want to comment, Sharon, that regarding your question, and then Oleg is going to ask, and then Sasha, that Paula Levisatos has actually fused assembled layers in a competing, I say, effort, where you don't form assemblies of dimers, you form assemblies of monomers, and then you fuse them to actually make good conducting materials, maintaining the properties of the building blocks, the optical properties of the building
Totally,
blocks.
the fusion of arrays is definitely interesting. I mean, I don't know if like combination of dimers and arrays, but definitely monomers, which we see a lot of superlattices over this week and in the workshop too, that the ability to fuse for semiconductors at least is quite useful, I think, because in one side the idea is to keep the quantum confined architecture, not lose it just by making a continuous film. Okay, one reason would be let's fabricate at very low temperatures, then we can make flexible things and so on. But also the other underlying thing is that we can really make a new material because we keep the quantum confined structure even if we fuse them and make like connecting necks between them. So the fusion chemistry that I'm very interested in is also relevant for arrays for sure. Yeah.
Yeah, thank you. Very interesting talk. I also have kind of a naive question, maybe to some degree. So, if I'm comparing, for example, the emission of a single quantum dot in the presence of, let's say, plasmonic particles, I would expect, depending on the distance and size of the plasmonic particles, enhancement, and so on. My question: to what degree you would expect some potentially other type of effect associated with your dimers? Particularly, for example, we had results showing that you can induce in an isotropic plasmonic field polarized emission of quantum dot. So now, since in this situation, I'm just kind of curious. Again, I can discuss with you more,
Sure.
But I'm curious what you would expect, kind of a bit less unusual for dimers in a plasmonic field.
Okay, so I will not talk about the plasmonic enhancement in this because let's say you could potentially link a metal with a semiconductor particle. Then you have to think about quenching versus plasmonic enhancement, which would be interesting. But about the polarization, so when we have these are word-side lattice, so there you have also the effect of the actual lattice direction to dictate polarization. So smaller particles have their polarization in the AB plane compared to the C-axis. Our dimers can link in various axes, which I did not go into this week, I did it last week, and that can affect the polarization for the word-side one. The place where we did see an effect was when we went to zinc blende particles of cat selenide, cat sulfide, which are tetrahedral pyramids, tetrahedrons, and then what we got was actually bow tie architectures. And in this bow tie architecture, because let's say in the zinc blende, one of the ideas was, hey, this has only 1-1-1 facets. Maybe we get 1-2-1-1 facets linking. Actually, it linked tip to tip because of the high reactivity of that tip region. And in this bow tie, we did see enhanced polarization for the dimer emission. The monomer in that case is not polarized. There is no preferred axis, but the dimer did show preferred polarization along the bow tie axis, in line with, I think, what you were asking about, if I understood correctly. Yeah.
Sasha?
Uri, I have two questions. One very short. In biexciton structure, in cat selenide quantum dot, there's biexciton structure. When you switch back and forth, do you see any signatures that it is split or
You mean you're talking about the electric field or the the experiment, the heralded spectroscopy? We did it at room temperature, so we cannot see. This is all broadened. I want to do it at low temperature. I have now. We bought a detector like this. This is out of the beta site.
Another question: how do you align your molecule along electric field?
So here we just, what we did so far was just spin coating, and we get different orientations, which we can actually verify with this correlation of the electron microscope with the optical measurement. But there is a way to align. For example, if you deposit while you have an applied field between the electrodes, for example, even an AC field can, during deposition of the drop, will align, the particles will align. This is, I mean, this was done with nanorods. We haven't done it with dimers, but this would be an idea how you would align. It should align. With rods it works. This I know, this I did before. We aligned a lot of rods this way. Yeah.
Yeah, beautiful talk here.
Yeah.
So my question is about the electric field induced color switching. Is that more of a binary process, or the color switching is actually a gradual process depending on, for example, the local electric field?
So it's an instantaneous effect, namely it's just the electron responding. Nothing has to move, not like liquid crystal molecule that has to move physically and so on. It's really instantaneous. And it's either on one side or the other side. You're saying what happens if, you can have a situation where the wave function is kind of undecisive. So we could have those intermediate regimes. In the simulation, we kind of see that. But experimentally, it's a single particle experiment. And we do see this change in relative weight of either side with different biases. But, during such an experiment, there is also these particles, it's single particle, you can get some charge on it, it can shift because of that, etc. So it's more difficult to see a continuous shift. At low temperature, we are aiming to do this also at low temperature, which could help to actually resolve some more gradual shifting effects.
I see. The reason I was thinking about that is because I was wondering if we can use it as a sensor for the local electric field.
Definitely.
For bioelectricity, for example, that would be great.
Sure. It could also, this effect might also be relevant as a sensor, going in line of what I showed briefly from, for example, what Sasha was proposing is using quantum dot as a sensor for electric field in neural science. Yeah.
We have 2 more questions, so let's start and maybe quick question answer. We have 2 minutes.
So first, beautiful structures, and so you chose to do fluorescence microscopy to characterize the changes in electronic structure, and you started your talk with STM. So I wonder if you're considering using some of those techniques to get insight into changes in electronic structure, not necessarily to see like non-emitting states and.
Exactly. So to do that, the best system to do that, you need, it's much better to do it in low band gap material, because the range where you can effectively apply the bias and still get tunneling currents and so on is, let's say, plus minus 2 volts maybe or so. And if you have a large gap, it's hard to see all those charging effects and so on. So it's not by accident that indium arsenide was chosen in the early work. And that's one issue. We want to make those. We haven't done that yet for indium arsenide. And second, my colleague Oded Milo, he had his lab move and so on, but we are in discussion to do also this to look really at just the electrons, like you suggest, yeah.
So I have also a simple question about the chemistry, which is that basically you have cadmium selenide and then you cover them with...
Use the microphone.
Sorry, you have this cadmium selenide and you cover them with a cadmium core.
Cadmium sulfide, yeah.
So cadmium sulfide. So the question I have is, let's say that you put that in a 2-dimensional lattice and you do the same thing covering the entire lattice. I mean...
Yeah, exactly.
So is that...
Completely, that was actually a topic that Eran mentioned, that Paula Levisatos and his group worked on this also with Eran, to take arrays and then do some chemistry to fuse them. And I'm quite certain that this is a possible thing to expand. They demonstrated successful fusion in some cases, etc. So this is an interesting direction to merge the two fields somehow, right? To take superlattice, which is known how to make now very nicely. We saw a lot of works on that topic. And now add this fusion element, where in my view, let's say once you have the shell material is going to be the one to fuse. The same material fusion is more easy than other materials, although this could be a second degree of complication or even further elaborate structures if you have different shells fusing. And you still have a core which emits, which can have charge going in and out, etc. So this would be very interesting systems in my mind for studies. Definitely.
Is it straightforward for you to do?
You should ask my students. It's
It's straightforward to put it in a proposal that we are writing. But
yeah, I think it can be done. Yeah, there are possibilities how to fuse. Yes.
Anyhow, I think we have to stop here. So let's thank Uri again.
Thank you.
And